Myself already. I will continue with the last one. And this is about automation. So I would like to get you in a little bit higher level, so in the whole machine application, actually on the whole business application, and then coming back to the requirements on the power generation in those machines, and where we really see the future and the resolves and the potential to change those things in the future. First of all, productivity. So we're talking about mobile machines. I was explaining the process is really what's the machine about, and not so much the mobility. Productivity in that agriculture business comes from working with the last 100 years. Working with higher operational speed and larger storage volumes. This is what you see, these characteristic numbers you see on every machine that has been built through the last 100 years. And actually in the last 50 years, the productivity growth in agriculture business was the highest compared to all the other industries. For two reasons, a lot of demand, and there was also a leaping behind up to the World War II, and then keeping up a lot. I'll talk to that a little bit later. Now, we really run into conceptual problems with those machines, since they are driving on the road as well in order to get to those places where they need to work. With that growth of working speed and working width, weight and dimension of those machines has come to a limit, and are really now a limiting factor. Today, because of a road regulation, but on the other hand, with the weight of those machines that they have today, we are actually doing also such a lot of soil compaction that is an even worse condition. So we're doing much more compaction in the soil than we actually doing damage to the road because of the machines. However, because we cannot measure soil compaction today, and we cannot measure the impact of yield reduction due to that soil pressure, we don't have the quantitative number for it. We only have qualitative numbers. So that will be part of the future for sure. So, but given that, the concepts are limited, weight and dimensions are at the end. Therefore, we have that major trend of automation in those machines, because that automation means high utilization of installed capacity. So we don't have to grow productivity, don't have to grow the size of the machine in the original manner, because we increase productivity by automation procedures. Now the question is, how do we get to cope with the problem of those dimensions? And there are different ways to approach that. First thing would be increased process density. So in the same envelope, doing just more processing, which means more power, which also means different functional components. And if we cannot increase process density enough, then we have to reduce the machine made, to increase the machine size, but have to reduce the machine made by lightweight design. We do the lightweight design with steel and higher strength materials. That's already today the business. What we really foresee in the future, 10 years from now, is the fiber composite stuff. If we will need to stay in the same concept, fiber composites need to come, because we cannot increase the weight of the machines anymore, but we have to increase productivity. So that's one thing. I was talking about automation. That is the second thing, but automation only carries for a while. If we getting closer to the 90% level of technical capacity, then automation is at its end anyway. And then there's also a lot of thinking, and I will show you some ideas of that. Those disruptive conceptual changes, so say we do machines totally different in the future. We go away from that growth rule of working with and installed engine capacity. We do different concepts in the future. And this would also lead to autonomous machines. So these are the things we are facing today, and certainly power generation in that process is a big question. How do we generate power? And if we change machine concepts, then the way to generate power may change, and what certainly changes is the way how the power generation is split up. If we're running to smaller units, then obviously our power generation units will be smaller again as well. I'll talk to that in a minute. Just looking what Berger Consultant is figuring out for the market, is pretty nicely shown at this chart here. It's really that bigger, faster, wider growth rule is now becoming is getting to smart and connected, still within the same concept, but what comes after the smart and connected? That's the big question. Just looking at the history a little bit, how history has been developing, you see this change from increasing productivity by coming from the muscle power to engine power. Then we had the tractor-pulled implements, and those tractor-pulled implements, if productivity needed to grow, then the implement became a self-propelled equipment. So not having the universal tractor providing traction and auxiliary power, and the operator station for the process, but getting the whole process embedded in one specific machine. And we are talking, like he was saying, you're talking about 250, 300, 400 hours a year for such a specific machine. So a combine harvester has usage hours of less than 400 hours a year. It's in Europe, we have 20 days for harvest. This is what we have a machine for, and it needs to pay back within those 20 days. So high range productivity within one machine, and it works at the moment. But we are concept limited, as I explained. So here the big question is, what do we do in the future? Just talking about revolutions, we had this revolution 2.0 with the introduction of the engine. Then we had the third revolution, with introduction of chemical fertilizers and plant protection. And today we are really at this industry 4.0, cyber-physical systems. We are seeing very much the same thing. We are talking about farm 4.0, transforming to digital farming in the future. This is just starting now. Certainly at a very high speed, because all that digitization technologies, they are on a very fast development path. So, and this digitalization, that leads us to automation at not only in a machine level, but on the farm level. And the big question for the future is, how is that historical development to self-propelled machines carrying forward? Do we really increase machine size even more and find solutions for it? From the engineering point of view, that is possible. Engineers always find solutions. But does it really make sense? And these are the most economically viable concepts, and there's a lot of doubt that they would be. It would be just the standard incremental improvement of machines coming to those giants, and there are already a lot of people and a growing number of people that are believing we will change that drastically, going to those swarms of dwarfs, of smaller machines, still increasing productivity. A word to digital technologies. As in other areas of the industry, this is also true for agricultural business. This will change agricultural production processes in an unprecedented way. However, if we don't do it right, it's not a given. It doesn't come in itself. It's very complex. It's very global, and there are lots of traps on that way to fail in that process for many reasons. So I would like to say it could change if we are doing it right. We will stay the old way and would see many problems and other scandals if we are not doing that the right thing. Just to mention a few of those technologies, 5G, that's the most important one. Actually, we have here at Dresden, we have the 5G lab of Germany, which are at least in Europe, the leading research center, not based in industries. We're working very closely together with them. It's just amazing what they provide in technology, and it carries you a way of thinking what we will do completely different in the future. Then we have all that other list of technologies of digitalization, which will be implemented in those machines in the future, and so we have all those building blocks to change our concepts in the future and to come from the single machine development to a machine, or even a process thinking, process automation. So that's just coming, and there's a lot of work going on, and that's all interdisciplinary work. So life is getting more complex, it's getting more harder. However, if we can approach that the right way, then it also is becoming much better for everybody. Talking about connectivity, here are the areas where we really want, where we think connectivity gets implemented. First of all, that makes sense, robotics and automation. So we have totally different ways to communicate between the process components. Not even saying machines, but communicating between the process components. We can carry that at the farm operation level. Also, if we're talking about automation, the development of sensors is a very important thing, because sensors will deliver the feedback of the process, will deliver the current status of conditions, and will also deliver us in the development phase the knowledge that we need in order to control our processes. And that may be going down even to the bioengineering part, where all the seeds that are used at the farm operation level are not only selected in a brochure and a catalog, but by more knowledge-based systems accomplishing all the different impacts in the farm operation and selecting the best possible seed in order to grow at the farm. So again, lots of opportunities out here to improve. Now I'm coming more to the engineering part. For engineering part, and it's true for every mobile working machine, construction, agriculture, or other areas, productivity, performance, quality, cost of ownership, that is what drives us forward. And whenever we come up with the next level of that machine system, we have been increasing one of those, or even better, all of these parameters for the customer. So we are thinking in that system of tractor and implement, or that self-propelled machine. But this is not enough anymore, because now we already understand that there's a process that was before my system, and there's a process that my system is following my system in that plant protection cycle. So the production system of a farm is producing biomass, producing plants, and we have all those different machines and equipments along that process that's usually somewhere around 180, 200 days in the year. So we have a system, and since we have all the technology building blocks and the sensors, lots of knowledge and a lot of information and data, we try to utilize the data of one step and deliver it to the next step in order to optimize the next step of operation as well. So things are getting more complex with that connectivity, lots of more potential, but also more complexity. However, this is still not enough by far, because then really the big thing is coming at us, and that's you recognize on CO2 reduction, you recognize that on emission control. We are seeing the same thing in order to really be sustainable and resource responsible, and not decreasing biodiversity even more compared to the level which is not sufficient today already. We have our machine system that's in that shell of the ecosystem, and all around we have that information level that is capable to connect everything and every unit to every possible information. This really makes development quite complicated, because now still the question stays, how do I position myself with new ideas that are still economically viable? Because at the moment, the way is, and we recognize that at every branch, that it is accepted on the market and can be sold to customers if it's economically viable. For the green part down there, everybody of us knows we need to address that. But as long as it's not economically viable, the only way to address it is by regulation. And regulation is limiting innovation big time. So we try to come up with ideas that to work on that green part in the whole system, still being economically viable. And there are some ways to do that, but it won't work without regulation. And What's coming on top of that is the gray part that basically takes place in a fiscal year. So it's a 1-year cycle, and the green part that is nature, that's ecosystem. Here we're talking about cycles of 30, 40, 50 years and more. So if we really do a lot of damage to the green part, we won't see it at the time we see it. It needs several decades to repair, which is you don't have a business case how to do that. So we need to address that. What everybody that's similar to Industry 4.0 or cyber physical systems, how it's called in North America. Our single machines will develop to systems of systems. I was explaining that. If you're looking at the market where we are today, that would be the judgment. Western Europe has technology leadership in agriculture business because of the stronger competition in the market. It's a technology-driven market, and that certainly results in new technology, new innovation is in the first place put into the market in Western Europe. North America follows short behind, and it's not because of their capabilities. They have the same capabilities or better. It's just because of the market demand. They can afford to leap a little bit behind Western Europe. Then Eastern Europe is very diverse. They run the best technology down to the 30, 40, 50 years old technology. That really depends on how the business is built. Is it a larger structure? Is it a smaller structure? Is it family owned? So they are broadband. And Asia usually is in technology behind 20, 30, 40 years about. And that's again, that throws up a very important question. I was showing you the historical development of the equipment. Is Asia, for example, following the same path? Do they, at the moment they do, they grow their tractor, they do grow their engine sizes, they grow their working widths. But since now we are at the basically at the limit of our concepts and think about new concepts, there's a certain and very interesting possibility that Asia is not following the whole path through to those big machines as we have it today, but switching over to the new concepts much earlier, but just skipping those large self-propelled equipments. Because if we get down to smaller units, then they fit to the structure of these farms much better. It's impossible on a 40 by 40 meter field to put a combine into that field which has a 12 meter working width. That's just totally impossible. So coming back to smaller units, that's interesting. They don't even follow the whole path. And with that modular thinking, it could also be scalable automation level, scalable drive technology. So also come up with a cost level that is achievable for those markets. Okay, now talking about potential for CO2 reduction, and that's what this summit here is about. Everything is about CO2 reduction, emission reduction. How do things get more efficient? How much fuel can we save with certain things? We're facing the very same thing here. But if you're looking, where's our potential in fuel reduction? Again, as I said, we have that process with us. And if you're looking at the cars and on-road business, they are somewhere around here in the upper level. And this is for us, for our potential, this is only 10%. Because at the machine functional level, so how is my process being done, and the process automation level, there's another 30 to 50% potential just to work more efficient, which means we're saving fuel, we're reducing CO2 emission. And then, but really the highest potential is on the farm operation level. Farm operation is done today more or less in a manual way in the communication device. For that is a cell phone. And so there is no automation at the farm operation level. Communication is really done manually. There are no databases, there are no SAP systems today that are carrying all the production data and allowing to get this knowledge standardized and put back into algorithms. That's a starting thing. They're called farm management systems, but this will come in the future. And everybody expecting from those farm management systems that do automate and assist the operation at the farm level with all that new technology, that there's a potential saving of input resources. So and this is something where we really can fit together the economically viable solutions with the environmental helpful solutions in that range. And but the big problem here is today we are thinking in machines, and we are evaluating machine performance coming down to that farm operation level. That would mean that we have to do an assessment of the production process in total. So not just one machine, one implement, or two machines. It's the whole growth period from seeding to harvesting would need to have an assessment in order to balance between the inputs and the outputs and the machine technology that's used for. We don't do that today. And this is not the way that the machines are sold today. So it would be a great cultural change for not only for marketing in the markets, also for the R&D departments, because now the development would take place outside the machine, inside the machine. And on the other hand, if we're really going back to try to assess our processes by creating some load cycle systems, because of the high diversity of processes and high diversity of markets, it's basically impossible to simulate all that here representative in certain load cycles, which is done today in the truck and car business. They just have the load cycles, and then the drivetrain is run against that load cycle, and the drivetrain is assessed according its emissions and values. If we are doing that, we are only at the upper 10% reduction potential, because then the rest of the world, the rest of the important world, is just put into one certain load cycle, which is always wrong and never true. But if that exists, and that's the big danger in regulation. Regulation at today's status would come down to creating some certain load cycle, and would drive us to increase efficiency of drivetrains of machines, would waste our engineering power and ideas, innovation in that area with the least potential. So from the overall point of view, this would be the very wrong thing. Now the big question is, how do we get out of that? We don't really have the best answers yet. One answer I'll show you in a second. That's just to support where we are in automation. The big problem is mobility is the smaller part. The really process power consumption is the bigger part of any emission, of any fuel consumption we do today. And for example, large machines like the flagship of forage harvester or flagship of combines, they have an 1,100 liter fuel tank with them, and they use it within 12 hours of work. So that's the amount of process power that is implemented. And that also makes it so complicated to go to alternative power sources. And electrification and any of that other stuff, so running by battery, running by fuel cells, running by hydrogen, that's all very complicated, because nothing today really reaches that energy density of fossil fuels. Still, that doesn't mean that I'm not convinced that we have to change it. It's just, it makes it complicated, and we need to, machine concept changes will help to address that problem as well. How do we get the power to the field? And today a customer is used to that his fuel tank lasts at least a day, and then he can get back to the farm and refuel the machine. And if we carry that paradigm forward, then we had awful sizes of battery packages or hydrogen tanks with our machines in order to allow that. But that's not a given. The question is, what's my productivity? What's my service time to refuel my machine? And if we find ways to do that in short times and without decreasing productivity, that's easy. Okay, here's one. I skipped this one. Oh no, that was hidden slide. Okay, going back. One approach that is taken is that ecotech project. I had a slide, but it's hidden at the moment. Ecotech project means there's an assessment of the production process, and that's all put into a simulation tool. And with that assessment and that simulation tool, it is supposed to be possible that the current status of CO2 footprint for a farm can be assessed, and then based on that current footprint, any activities in the future to reduce this current footprint can be shown as well. And this is intended to be, and the VDMA is driving that, and the industry is driving that approach, and it's a group of industries and a group of research units that are driving that project forward. And the whole intent is to come to a self-assessment of the industry and to documentation of how many CO2 reduction can be done by changing the processes in order to avoid that regulation part. Because with that way it could be shown that the whole agriculture business is capable to reduce emissions and can document how much that has been done, just at a much higher level of complexity. So that's at the moment the way how we think we can approach that CO2 reduction problem. So back to what will the future bring to us with the step to cyber-physical systems. The cyber-physical system is nothing else than a physical system connected to the outside world with those technology means. We are facing still the same automation task as we do today, but what's coming on top of that is that security and safety problem. We didn't have that before, as long as the communication was inside the machine, which is currently in most of the cases true. If you're going outside of the machine with communication, we will have to face that security and safety problems. And it's not the machine manufacturers that have the competence doing that, it's the provider of digital technologies that have to provide us that. But talking about 5G mobile communication, safety, security is reliability, latency, that's all built into this into these systems in a completely different manner as we have it before. So it's not comparable to our cell phone mobile communication of today. That's one side, and on the other side, with changing concepts, changing machines, being in a new environment, and a mega trend in the world to healthy food, to food with less meat, that all impacts the business a lot. So there are lots of ideas how to come up with new business models of regional food providing, which will impact the farm operation, which then will impact how the requirements, how to do those machines. And coming from the manufacturer engineering side, we want to really know very early what is that with those new business models, and how do we help them to establish them, and how do we make our machines profitable in that new world. And last but not least, what's very important is that human-centered design. Automation, if we drive automation forward as we do it today, we basically would remove the human out of the system. So far we have been very, very successful doing that. Whenever we do an automation feature, helping the human, productivity, reliability, quality was better than afterwards. And operators were basically satisfied that they have been delegating a task to the machine is doing that much better. But now we're coming to a level of automation where it's not a lot left over. And there's a certain dilemma of automation. Automation helps the operator, but on the other side, by helping him doing things, operators lose their capability because they don't learn how to do things anymore. So even if you put a good operator on a very high automated machine system, his competency will reduce, will decrease. That's how the human brain is working. If we don't practice things, then we just start to lose it. So with the automation procedures as we do them today, we just consider humans as disturbance in the system and try to automate the systems in a way that we can live with those disturbances and try to eliminate those disturbances as much as we can, which really means we run into the dilemma of decreasing competency of our operators. And now the point is, in our business here, 100% automation with all those diverse processes and all those disturbances coming from natural materials. There are two schools. One school is saying we will be capable to do 100% automation and completely remove the human out of the machine. That's basically common sense. But there's also another school saying we are not capable, from the engineering point of view, we are certainly capable to automate everything, even 100%, but it won't be economically viable because we need such a lot of sensors, such a lot of knowledge, such a lot of testing to implement that compared to the labor cost, which is in today's system, it's less than 5% is labor cost in the business. So let's better think about to not consider humans as a disturbance, but consider them as a very intelligent means to automate the system in all those cases where our standard algorithm, which is very effective and very economical, doesn't have a solution. So this would allow us to get to that 90-95% level of automation and then hand over to the operator for the last 5% of any other problem. We don't need to figure out what it is because humans are usually much better doing that. So that is a very important point because this will decide if we run down that 100% automation path and consider this is economically not viable, we're having a problem because we don't get back as easily. And looking at the building blocks for future machines, looking at that automation level, then this is Berger Consulting. They put together all those technology blocks that are already existing. And first thing, there are a lot of technology blocks that we need in order to come to automated systems. But there are also, this is high complexity, but on the other side, they are existing. And Berger Consulting, they are saying we don't get our ultimate final eventual target is not the robotics, but the cobotics. And cobotics is defined with collaboration of human and machines. That's what I just explained. We consider the operator a part of our controlling system and not as a disturbance. And so these humans can collaborate with the machine system. Again, from the point of automation, it's not so complicated. It's just a different approach we have to take. And specifically in the mobile working machines business, with all those diverse processes and diverse markets, that really makes a lot of sense to have that human intelligence built into the system and make use of it and even make it scalable. That's what this picture is showing here. So there are different levels of how to automate. I wouldn't go into the detail if you don't have questions to it. The point is here on the right-hand side, between manual operation and full automation, we make that scalable with those collaborative systems. So it's not one certain level of automation we deliver with the machine. This level of automation is configurable per situation and per operator. So that's a totally different thinking in automation. However, methods, tools, simulations, knowledge, which is based on that, that's the same as today. It's just we put the human operator as another variable into the system and make use of it. And as it's a variable, it can be a very competent operator, can be an incompetent operator. We can slide this automation level up and down and utilize the system the best way without getting stuck at those conditions where 100% automation for some reason doesn't work and then causes the machine downtime. So that's the idea. And how, I think, and the very last one is an impression of those disruptive changes in conceptual thinking of machines. So how to get from the bigger, faster, wider paradigm to using that smart and connected knowledge and experience to new machine concepts, which would be still driven. We still have the operator out in the field, but but we don't have anymore that one-to-one connection, one operator, one machine. We have one operator supervising a number of machines. And then because he is supervising a number of machines, these machines could be smaller, which allows us to scale the productivity of the whole system by a number of units. And we cannot do that today. That's a big limitation. In a way, as we grow our machines bigger and bigger, the minimum productivity is set by the machine size. That's always true. And as it grows, the minimum productivity grows as well, which causes problems in smaller infrastructures because that high level of productivity cannot be utilized anymore, which causes the manufacturers to have now to broaden their range from very small productivity machines to the very high productivity machines. Now we narrow down that band of machines needed because productivity can now be scaled by number of machines. They're doing still the same function. There's still the operator supervises the number of machines as he would using one machine, and they have a very high automation level at the component level, but the operator's still out there in the field doing the supervising, doing the strategy, fixing any kinds of certain problems. So it's not remotely controlled, it's controlled at the site from the operator station. On these smaller size, the machine size you see here, that's about the machine size from 30 years ago. So this would be also the machine size which is currently used in the Asia markets, and that's the potential of those systems. They're not fancy, highly integrated technology machines. They are simple machines with an automation level that can be scaled to the market and then delivered accordingly. That's our ideas for the future. There are more and more people thinking the same way, and there are lots of advantages with these machine concepts. However, it's completely unproven if they are economically viable. Today, still the growth rule is true. Whenever 3 machines get replaced by 2, it's economically advantageous for the owner, for the farm. And really the huge challenge is using all those technologies, using human-centered design of cyber-physical systems, but make the whole thing economically viable. We think that can be done, but that's still, I would say, 10 years out from now. However, on the other side, with development cycles of 5 years for agricultural machines, this is basically the model after the next model. So looking from an advanced development point of view, it's right now time to get started with that. And what's also interesting, whenever you see those ideas floating around, they have always electrified drivetrains with them. Okay, so I think that's it for today. Thank you for your attendance. If you have questions, you can ask them. I'm lucky to answer them. Otherwise, we are done with that session here. And I thank you.